Welcome back, learners.
Yes, welcome back to another All Sorts podcast deep dive.
If you're enjoying this exploration of knowledge, we'd really appreciate it if you'd hit that like button and subscribe to our YouTube channel.
And don't forget to share it with your fellow learners too. Spread the knowledge far and wide.
Absolutely. And while you're at it, why not check out our treasure trove of past deep dives? We've got an incredible archive of episodes covering a vast array of fascinating topics just waiting to be discovered.
And to stay up to date with all our latest content and insights, be sure to follow All Sorts Podcasts on X, Instagram, and Threads. We're always sharing something thought-provoking.
Today, we're diving into the intricate world of TCP/IP, the very foundation of the Internet as we know it. It's a topic that might seem a bit technical at first glance, but trust us, it's absolutely fascinating once you start to unravel its mysteries.
Indeed. We have a collection of illuminating sources before us, ready to guide our exploration. We'll be drawing from the ever-reliable Wikipedia entries for both the Internet Protocol Suite and the Transmission Control Protocol, along with insights from TechTarget, Fortinet, and A1 Digital, all recognized names in the world of technology.
Our mission today is to distill the key takeaways from these sources and present them to you, the learner, in a way that's both insightful and engaging. We'll cut through the jargon and highlight those aha moments that will leave you with a solid grasp of what TCP/IP is, how it works, and why it's so fundamental to our digital lives.
And perhaps even more importantly, we'll explore why this knowledge matters to you and how it affects your daily interactions with the online world.
So let's begin our deep dive with the most fundamental question. What exactly is TCP/IP?
Well, TCP/IP, or to use its full name, the Transmission Control Protocol Internet Protocol, is essentially a set of rules, a framework, a suite of communication protocols that dictates how computers talk to each other over the Internet.
It's the language of the Internet, so to speak.
Precisely. And it's organized based on function. Imagine a toolbox filled with various tools, each designed for a specific task. That's a good analogy for TCP/IP. The Wikipedia entry for the Internet Protocol Suite highlights the three most fundamental protocols within this toolkit: TCP itself, the User Datagram Protocol, or UDP, and the Internet Protocol, IP. These three form the backbone of most Internet communication.
So it's not just one big monolithic protocol, but rather a collection of specialized ones working together.
Exactly. It's a beautifully designed system where each protocol has its specific role and responsibilities.
Now, I've always been curious about the history of TCP/IP. How did this foundational technology come to be? It seems like something so deeply embedded in our digital lives must have a fascinating origin story.
It does indeed. And you might be surprised to learn that it has roots in the military. Early versions of this networking model were known as the DoD model, standing for the Department of Defense. The initial development was heavily funded by the U.S. Department of Defense through DARPA, the Defense Advanced Research Projects Agency. As you might imagine, they were looking for robust and secure communication networks for military purposes. It's quite remarkable how a technology born from such specific needs ended up becoming the foundation for the global internet we all use today.
That is fascinating.
Yeah.
From military applications to connecting billions of people worldwide, it's a testament to the power of innovation and how seemingly specialized technologies can evolve to have such a profound impact on society.
Absolutely. Now, let's delve a bit deeper into how TCP/IP actually works. Imagine TCP/IP as a sort of invisible conductor orchestrating the flow of data packets across the internet. It acts as an abstraction layer between the applications you use, like your web browser or email client, and the complex underlying network infrastructure of routers and switches.
So it's like a universal translator, ensuring that all these different devices and applications can seamlessly communicate with each other.
Precisely. TechTarget describes it quite well as an abstraction layer. TCP/IP defines the entire life cycle of data as it traverses the network. It specifies how data should be broken down into smaller units called packets, how those packets are addressed with the correct destination information, how they're transmitted across various networks, routed through different devices, and ultimately received and reassembled at the intended destination. It's a remarkably efficient and robust system.
It's like a highly sophisticated postal service for the digital realm, ensuring every piece of information reaches the right online address in the correct order.
A very apt analogy. And here's a crucial point that TechTarget emphasizes. TCP/IP is designed to operate with very little central management. It's inherently a distributed system, which contributes to its resilience. Even if a particular router or network segment fails, the protocols can often automatically reroute the data packets through alternative paths, ensuring that the communication continues uninterrupted. This inherent fault tolerance is one of the key reasons the internet has proven to be so reliable and adaptable.
That's incredibly important, especially in today's world where we rely so heavily on constant internet connectivity. It's like having a backup plan built right into the system itself.
Exactly. Now, you might be wondering who's responsible for maintaining this intricate set of rules, ensuring that everything works smoothly across such a vast and diverse network.
Right, it sounds like it could easily become a chaotic free-for-all without some central authority overseeing the process.
Well, there is a governing body, but it operates more as a collaborative organization than a strict enforcer. The technical standards for the entire Internet Protocol suite, including each individual protocol within it, are meticulously maintained by the Internet Engineering Task Force, or IETF. This group of experts from around the world collaborates to ensure interoperability between different systems and oversees the ongoing development and evolution of these core technologies.
So it's a collaborative effort to keep the internet functioning as a unified whole.
Precisely. And it's worth noting, as both Wikipedia entries point out, that TCP/IP actually predates the OSI model, which is another commonly referenced framework for describing network communication. The OSI model, with its 7 layers, is a bit more comprehensive and theoretical, while TCP/IP, with its 4 layers, is more pragmatic and implementation-focused. It was developed first, driven by practical needs, and the OSI model came along later as a way to standardize and categorize networking concepts more broadly.
So TCP/IP is the real-world workhorse, while OSI provides a more abstract framework for understanding the bigger picture.
That's a good way to put it. Okay, now let's take a quick but fascinating journey back in time to explore the historical origins of this remarkable technology. The development of TCP/IP is deeply intertwined with the very early days of computer networking.
Yes, I always find it fascinating to trace how these groundbreaking technologies we rely on today emerged from those early research efforts.
Absolutely. The Wikipedia timeline highlights that the initial seeds were sown in the 1960s with pioneering networking concepts developed by the RAND Corporation and ARPA, the same organization that later funded the development of TCP/IP. These were the very first theoretical explorations into how different computer systems could potentially communicate and share information.
And then came the ARPANET, often hailed as the precursor to the modern internet.
Precisely. The ARPANET, launched in 1969, was a groundbreaking demonstration of packet-switched networking, where data is broken down into small packets and transmitted over a network of interconnected computers. It served as a vital testbed for many of the ideas that would eventually coalesce into the TCP/IP protocol suite.
So it was a period of experimentation and refinement, leading to the formalization of TCP/IP in 1982.
Exactly. That standardization was a crucial step in solidifying the basic architecture of what would eventually become the global internet. And it's interesting to note that the original encompassing transmission control program was actually split into 2 distinct protocols, TCP and IP, around 1978, with the emergence of version 4. This separation of responsibilities, with TCP focusing on reliable data transport and IP on addressing and routing, proved to be a wise architectural decision.
It's like dividing a complex task into specialized roles, each handled by a dedicated expert.
Precisely. And another significant influence on the design philosophy was the end-to-end principle pioneered in the Cyclades network, as Wikipedia mentions. This principle essentially advocates for keeping the core network infrastructure relatively simple and focused on efficiently transmitting data packets. More complex functionalities, such as error detection and recovery, are then delegated to the end devices themselves, the hosts.
That makes sense. Keep the core network lean and mean, and let the devices at either end handle the more intricate details.
Precisely. It contributes to the network's overall robustness and adaptability. And then, as we mentioned earlier, the U.S. Department of Defense made a significant commitment to TCP/IP in March of 1982, declaring it the mandatory standard for all military computer networking.
That was a pivotal endorsement, propelling TCP/IP toward wider adoption.
Absolutely. And then came Flag Day on January 1st, 1983, when the ARPANET fully transitioned from its older NCP protocol to TCP/IP. This marked a decisive turning point in the evolution of the network, cementing TCP/IP as the dominant protocol.
It's like a symbolic changing of the guard, ushering in the era of TCP/IP.
Exactly. And from there, the commercial adoption of TCP/IP accelerated throughout the 1980s, driven in part by a series of workshops promoting the technology to industry leaders.
And I recall reading about the role of Trumpet Windsock in bringing TCP/IP to the masses.
Yes, Trumpet WinSock was a crucial piece of software. It enabled Microsoft Windows 3.1 users, who were the majority of home computer users at the time, to utilize TCP/IP over dial-up connections. It was a vital step in making the internet accessible to a much broader audience.
From its origins in military research labs to becoming a key enabler for everyday computer users. It's an incredible journey of technological evolution and democratization. Okay, now that we have a good grasp of the historical context, let's dive into the heart of the matter. TCP and IP themselves. We always hear them mentioned together, but they clearly have distinct roles. Let's break down those differences and how they collaborate to make internet communication possible.
Absolutely. Let's start with TCP, the Transmission Control Protocol. As TechTarget aptly explains, TCP is all about ensuring the reliable and orderly delivery of data packets across the network. It operates as a higher-level, more intelligent protocol that relies on the underlying IP for the actual transportation of the data.
So if I click on a link in my web browser, TCP is the one making sure that my request reaches the web server correctly and the server's response gets back to me without any errors or missing pieces.
Precisely. TCP understands the entire data stream needed for that communication. It takes charge of segmenting larger messages into smaller packets, ensuring that all packets are sent and received, and then reassembling them in the correct order at the destination. It also defines how applications establish and manage dedicated communication channels across the network.
It's like a meticulous logistics manager, ensuring every piece of data arrives at its destination intact and in the correct sequence.
That's a great analogy. And in the 7-layer OSI model, which provides a framework for understanding network architecture, TCP operates at layer 4, the transport layer. This layer is responsible for providing end-to-end communication between hosts.
So TCP is focused on getting the data reliably from point A to point B, no matter what obstacles it might encounter along the way.
Exactly. And as Fortinet points out, TCP is a connection-oriented protocol. This means that before any data is exchanged, TCP initiates a connection between the sender and receiver through a process called a three-way handshake.
A handshake? That sounds a bit formal for computers.
It is, but it's a crucial step to ensure that both sides are ready to communicate reliably. Think of it as a way for the sending and receiving devices to acknowledge each other before they start exchanging data. TCP also actively manages the rate of data flow to prevent congestion. It can instruct the sender to slow down if the receiver is getting overwhelmed.
That's like having a traffic cop on the digital highway preventing data collisions.
Exactly. Now, what about errors? Does TCP just cross its fingers and hope everything arrives perfectly?
That would be a recipe for disaster, especially considering the complexity and scale of the internet.
You're absolutely right. TCP has robust mechanisms for error detection and correction. If a packet is lost or corrupted during transmission, which can occasionally happen, TCP will automatically request a retransmission. This is known as positive acknowledgement with retransmission. The receiver sends back an acknowledgement for every packet it receives correctly, and if the sender doesn't receive an acknowledgement within a certain time, it assumes the packet was lost and resends it.
So it's continuously double-checking and fixing any errors along the way. That's reassuring.
Precisely. TCP also uses sequence numbers to keep track of the order in which packets are sent. If they arrive out of order, which can happen due to different routing paths, TCP uses these numbers to rearrange them correctly before passing the data to the application. It's like having a meticulous librarian putting all the books back in the right order on the shelf.
It's truly remarkable how TCP manages all these intricate details behind the scenes, ensuring reliable data delivery even in the face of network hiccups.
It is, and it doesn't stop there. TCP also implements flow control mechanisms, often using a technique called a sliding window, and a range of congestion control algorithms, such as slow start, congestion avoidance, fast retransmit, and fast recovery. These mechanisms are crucial for optimizing network performance and preventing the whole system from collapsing under heavy load.
So TCP is like a highly skilled air traffic controller, keeping the data flowing smoothly and efficiently across the vast airspace of the internet.
That's a great way to visualize it. Now, let's turn our attention to the other half of the duo, IP, the Internet Protocol.
Right, IP, the often unsung hero of the internet. What's its primary role in this partnership?
Well, IP, as TechTarget clearly explains, is the more fundamental, lower-level protocol that handles the actual delivery of individual data packets. Its primary job is to get each packet from a source to a destination. Each packet has a header containing routing information, including the source and destination IP addresses and the actual data payload.
So IP is like the postal worker who delivers the mail, focusing on getting each individual envelope to the right address.
Exactly. IP defines the system of addressing used on the internet, the IP addresses, and it's responsible for routing those packets across potentially numerous interconnected networks. Each router along the way examines the destination IP address and decides the best path to forward the packet, getting it closer to its final destination.
It's like having a network of GPS-enabled delivery trucks, each one making sure the package gets to the next stop on its journey.
A perfect analogy. And in the OSI model, IP operates at layer 3, the network layer. This layer is responsible for managing the connections between different networks and ensuring that data can be routed across them.
So IP is the network navigator, figuring out the optimal route for each data packet.
Precisely. Now, here's a crucial distinction between TCP and IP. IP is connectionless. Unlike TCP, it doesn't establish a connection before sending data. It simply sends the packets on their way and doesn't guarantee delivery or provide any error checking. It relies on higher-level protocols like TCP to handle those aspects.
So IP is like sending a letter without a return address or tracking number. You just hope it gets to its destination.
Exactly. That's why TCP and IP work so well together. TCP provides the reliability and error correction that IP lacks. Conversely, without IP's addressing and routing capabilities, TCP wouldn't know where to send the data in the first place.
It's a perfect example of how two different but complementary approaches can combine to create a powerful and effective system.
Absolutely. Now let's shift gears and talk about the TCP/IP model itself. We often hear it described as having 4 layers. We've already touched upon the transport layer, where TCP operates, and the network or internet layer, home to IP. What about the other 2?
Yes, I'm curious to understand how these different layers fit together to form the complete TCP/IP stack.
Absolutely. The TCP/IP model is a layered architecture, with each layer providing specific functionalities and building upon the services of the layer below it. At the top, we have the application layer. This is where your everyday internet applications like web browsers, email clients, file transfer programs, and many others reside. The protocols at this layer include familiar names like HTTP for the web, FTP for file transfer, SMTP for email, DNS for resolving domain names, DHCP for assigning IP addresses, and a whole host of others. The data at this layer is simply the application data itself.
So when I type a web address into my browser, the application layer is where that request originates, and then the lower layers take over to handle the actual transmission and delivery.
Exactly. The application layer relies on the transport layer directly beneath it to manage the end-to-end communication between the hosts. We already talked about TCP, but there's another key player at this layer, UDP, the User Datagram Protocol. UDP is a connectionless protocol that provides a faster but less reliable service than TCP. It's often preferred by applications where speed is paramount, like video streaming or online gaming.
So UDP is like sending a telegram. It's fast, but there's no guarantee it will arrive.
That's a good analogy. Now, below the transport layer, we have the internet layer, where IP resides. We've already covered IP in detail, so you understand its crucial role in handling addressing and routing. Another important protocol at this layer is ICMP, the Internet Control Message Protocol, which is used for sending error messages and diagnostic information between devices.
So ICMP is like the network's alarm system, alerting us when something goes wrong.
Exactly. And finally, at the very bottom of the stack, we have the network link layer, also known as the data link layer or network interface layer. This layer is responsible for physically transmitting data across a specific network link, such as an Ethernet cable or a Wi-Fi connection.
So it's the layer that deals with the nuts and bolts of actually moving the data bits from one device to another.
Precisely. Common protocols at this layer include Ethernet, which is the dominant standard for local area networks, ARP, which helps resolve IP addresses to physical MAC addresses, and PPP, which is often used for dial-up connections.
It's amazing how each layer builds upon the one below it, creating a complex yet harmonious system for internet communication. Now, we've touched upon the importance of TCP/IP throughout our conversation, but let's explicitly reiterate why this protocol suite is so fundamental to our digital lives.
It's no exaggeration to say that TCP/IP is the bedrock of the internet. Without it, the internet as we know it simply wouldn't exist. It's a non-proprietary standard, meaning no single company or entity controls it. This open nature has fostered innovation and facilitated widespread adoption.
That openness has been crucial to the internet's success as a global platform for communication and collaboration.
Absolutely. And as TechTarget points out, TCP/IP is compatible with practically every operating system and a vast range of hardware and network technologies. It's also highly scalable, able to efficiently handle the immense traffic flowing across the internet.
That scalability is essential, given the exponential growth of the internet over the years.
Precisely. Now let's shift gears to a less comforting but equally crucial aspect: security. As Fortinet highlights, data packets transmitted over basic TCP/IP are inherently not private.
That's a concerning thought. It implies that our online communications could potentially be intercepted and read by unauthorized individuals.
Yes, that's a real risk, especially when using public Wi-Fi networks. That's why encryption technologies like VPNs and TLS/SSL are so important. They add a layer of security by encrypting the data being transmitted, making it much more difficult for eavesdroppers to decipher.
So the HTTPS, the beginning of a web address, signifies that extra layer of security.
Exactly. It means the communication between your browser and the web server is encrypted. Now, it's also important to be aware of some of the known vulnerabilities associated with TCP/IP.
Right. No system is perfect, especially one as complex as the internet.
Precisely. The Wikipedia entry on TCP mentions several vulnerabilities, including denial of service attacks, connection hijacking, and TCP veto, which involves injecting unauthorized data into a data stream.
Those sound like serious security threats.
They can be, but thankfully, security measures have evolved to address these vulnerabilities. For example, initial sequence numbers in TCP connections are now randomized, making it much harder to predict them and hijack a connection.
That's good to know.
However, it's still essential to follow basic security best practices like using strong passwords, keeping your software up to date, and avoiding suspicious links or attachments.
Right. Personal vigilance is always crucial in the digital world. Now, I get the sense that TCP/IP is not a static entity, but rather a constantly evolving system. The outline mentions ongoing development and evolution. What are some of the key areas of activity?
Yes, TCP/IP has undergone numerous refinements and enhancements over the years, driven by the need for greater performance, security, and adaptability. The Wikipedia entries mention a vast number of RFCs, or requests for comments, which document the Internet standards and protocols. Landmark RFCs like 675, 793, and 1122 represent key milestones in the development of TCP. This evolution continues today with ongoing research and proposals for new features. For example, TCP Fast Open aims to speed up the establishment of TCP connections. Multipath TCP allows a single TCP connection to utilize multiple network paths, and various congestion control algorithms are continuously being refined to optimize network performance.
It sounds like the IETF, the Internet Engineering Task Force, is playing a crucial role in shepherding this ongoing evolution.
Absolutely. They're the keepers of the standards, ensuring that the internet continues to function smoothly and adapt to new technologies and challenges. And it's worth noting that new transport layer protocols are emerging, such as QUIC, which is now being used by HTTP3, the latest version of the web's core protocol. QUIC incorporates features from both TCP and UDP, aiming to provide faster, more secure, and more efficient connections, particularly for mobile devices.
It's fascinating to see how the Internet's underlying protocols are constantly being refined and even reinvented to meet the demands of a rapidly changing digital landscape. Now, for a very practical question, how does someone find their own TCP/IP address?
It's actually quite simple. Your public IP address, the one that identifies your network to the rest of the internet, can be found using various online tools. A quick search for "what is my IP address" will usually do the trick. You can also often find it by accessing your router's administrative interface, which usually involves typing your router's IP address into your web browser. That interface will show your public IP address and other details about your network configuration.
So the router is the gatekeeper for my home network, assigning private IP addresses to my devices and handling the communication with the outside world.
Exactly. It performs network address translation, or NAT, allowing multiple devices on your local network to share a single public IP address.
That makes sense. It's like having a building with a single street address but multiple apartments inside.
A perfect analogy. Finally, let's wrap up with a brief comparison between the TCP/IP model and the OSI model, which we've mentioned a few times.
Yes, I'd like to get a clearer picture of how these two networking models differ.
Certainly. The most fundamental difference is in the number of layers they define. TCP/IP has 4, while OSI has 7. The OSI model, as TechTarget and A1 Digital highlight, is more detailed and theoretical, with separate layers for functions like data formatting, encryption, and session management. TCP/IP combines some of these functions into a single layer. Essentially, TCP/IP is more pragmatic, focused on real-world implementation, while OSI is more abstract and conceptual.
So TCP/IP is the practical engineer, while OSI is the theoretical architect.
That's a good way to think about it.
Well, the learner, we've covered a lot of ground in our deep dive into TCP/IP. We've explored its origins, its inner workings, its strengths, its vulnerabilities, its ongoing evolution, and its relationship to other networking models.
Hopefully, you now have a deeper appreciation for this remarkable technology that underpins our digital lives.
It truly is amazing how TCP/IP seamlessly orchestrates the flow of information across the internet, enabling us to connect, communicate, and collaborate on a global scale.
And it's a reminder that even the most complex technologies are built upon foundational principles that are often surprisingly elegant and intuitive.
Now, as we conclude this deep dive, we encourage you to continue exploring the world of TCP/IP and the broader field of networking. There's always more to learn, and a deeper understanding of these fundamental technologies will only become more valuable as our reliance on the internet continues to grow.
What new innovations will emerge in the realm of internet protocols? How will TCP/IP adapt to the challenges of emerging technologies like artificial intelligence, the Internet of Things, and quantum computing? These are fascinating questions to ponder as we navigate the ever-evolving digital landscape.
Thank you for joining us on this journey of discovery. Until next time, stay curious, the learner.